My name is Jan. This talk might be a bit of a curveball for this conference at all, but I hope it's still interesting to you. I want to preface this by saying I am not an expert in spiking neural networks, or I am a complete novice in neuromorphics. My field of expertise is actually medical imaging, medical physics, and specifically positron emission tomography, which a large part of this talk is going to be about. So you might take this talk a bit as the perspective of an outsider looking to use neuromorphics to try to do something in their field. Yeah, I don't expect anybody here to be an expert on positron emission tomography either. So I think I'm just going to start this off by showing you a little bit about my field, giving you a little bit the basics, because it's a bit integral to what we've done. Positron emission tomography is a medical imaging technique. Some of you might have already undertaken a CT or a PET or an MRI scan at some point in their lives. Those are medical imaging techniques which focus on giving you an overview of the anatomy of a patient's body. PET is slightly different. It's a functional imaging technique. It gives you an overview over the location of metabolic processes within the body. The best way to usually explain this is just with an example. One of the most commonly used PET tracers is called FDG, or fluor desoxyglucose. This is a radio tracer consisting of a combination of a radioisotope, so a radioactive element, combined with a metabolic substance, in this case, glucose. If you inject this into a human's body, this behaves pretty much exactly like regular glucose. So it starts to accumulate in regions of the body which consume a lot of glucose, like the heart or the brain or, well, a cancer cell. The reason why this is interesting is that after this is accumulated, you can then look at the radioisotope, which decays. Fluor-18, which is used here, is a beta plus emitter. So when it decays, it emits a positron, which pretty much immediately annihilates with an electron in the surrounding tissue. And the result of that is two photons of a very specific energy, which are emitted at pretty much exactly the opposite angle of one another. So they fly off in opposite directions. And that is helpful for us because if we build a detector around our patient with scintillating crystals, then we can detect these photons. And if we detect both of them, then we can know, okay, somewhere along this line, there must have been our tracer. And if we do this and repeat this 1 to 10,000 times, and look at all these coincidences, these coincident events that we've detected, and look where they intersect, then we can kind of gather, okay, somewhere here our radio tracer must be. So that's where our cancer cell must be. This, of course, is a bit of an abbreviated, large overview over the entire thing. I want to focus today on a very specific part of it, and that is what is known as the coincidence sorting algorithm. These photons, which we see, we can't detect all of them. We have a certain detection efficiency, so sometimes some of these get lost. Also, when we detect them, we don't immediately see, okay, here this is our coincidence, but we detect the individual photons with some time shift to one another. Because of all of these things, with all our incoming data, we need to have some form to make sure, okay, we have individual detected photons in all these crystals. Which of these are coincidences, which we can then use to, well, get our tracer back? Regularly in PET, there's a classical analytical algorithm, which is known as the single coincidence window sorting algorithm, which is very commonly used in a lot of PET. And it's based on taking these individual events, each of these arrows is essentially an incoming photon, sorting them in time, and then evaluating them sequentially. We have a fixed timing window that we apply, and then we say, okay, we have here a photon. Is within our timing window another photon that arrived within that time? If yes, this is a type 2 event, this is a coincidence, this is what we want. If not, then it's a type 1 event, we can't use this, that's not a coincidence. There's also, of course, the option of having several decays very shortly after each other because it's radioactive decay. And because of that, we can have events where we have triple photons, which are not usable because we don't know which of these is the coincidence. This algorithm is very much established. A lot of PET uses it, but it has a slight problem, specifically at higher data rates, at higher doses, which is specifically the case in the project that I do. that it just becomes very slow. It it takes every individual photon and processes them one after the other. And if you have a lot of data, well, that takes quite a lot of time. So our idea was, can we use neural networks in general to maybe accelerate or improve this process? And we looked at several neural network architectures, and most of them didn't really apply. A regular fully connected artificial neural network doesn't work. LSTMs didn't really work. Transformers didn't really work. And then we looked at spiking neural networks and thought, hold on, each individual photon is just like, this stuff is just sparse, binary, time-encoded data, which arrives from our detector. That's kind of what spiking neural networks should be good at, right? And that idea in general is just what gave rise to what we lovingly dubbed PETNet. The idea is very simple. We build a fully connected spiking neural network with the number of input neurons and output nodes being the same as the number of crystals we have in our detector. And the individual photons that we have are just our input spikes, with our label data, or the output spikes, being the individual photons that are actually part of a coincidence. So what we decided to do is we simulated PET data so that we know both the inputs and the actual coincidences we can detect. And then we implemented a spiking neural network like this using SNN torch and the leaky integrating fire neuron. And yeah, that is basically it. It's a very simple idea, but to be fair, there's a few caveats. There's a few things we need to do first before that properly works. One was the loss function. From at least the loss functions we saw in SNN torch in general, we couldn't really use much of it. One would assume that like binary cross entropy loss is like the dead ringer for this, but it just turns out this doesn't converge. Maybe because of the sparsity of the data, maybe because of other things, it just didn't work. So we decided to, well, build our own loss function. This loss function, in this case, is just a linear combination of two separate things. One is the mean square error of the number of spikes we have per crystal, to just make sure that in each, well, crystal, in each output neuron, we have the exact number of spikes we want to have. And then the second part is the mean square error of the timing difference between predicted and incoming coincidence hits that we have. We weighted these at a factor of 10 to 1 and then applied that. The other thing is, due to kind of the nature of PET, that you have photons which are emitted in opposite directions of one another, you can kind of know where roughly you would expect another photon to occur if you have a coincidence. So we can actually supply our neural model, our spiking neural network, with the detector geometry by just adding additional input spikes on a separate layer of input neurons and then working with that. Our hope was to help the SNN that we train with its convergence with this way a bit. So we decided to compare it once with this geometric modeling and once without it. When it came to the actual training and the actual experimental evaluation, we decided to go for two data sets, which we start to simulate. One, which we call the clinical data set, used a smaller number of crystals and a smaller number of dose. That translates to less input and output neurons and less incoming spikes. And the other one, which we dubbed Sapphire, which is the system I work on, which has more crystals and a much higher data rate, a much higher spike rate. As I mentioned, we tested this with and without geometric features, so more input neurons on less input neurons. And we simulated about 60,000 samples with like a 80-20 train validation split. And we trained this with the Atom optimizer using just one hidden layer. Did a bit of hyperparameter optimization up front. In this case, just with the clinical data set because it was smaller and easier to do. And then we translated those hyperparameters also to the other data set, to the Sapphire data set. That is basically it. And the results, to be fair, were quite surprising. We decided to evaluate the results of our spiking neural network in comparison to the classical single coincidence window sorting algorithm using the F1 score, which is just the harmonic mean of the precision and accuracy, which are values calculated from the number of true positives, false positives, and false negatives we see. And if we look at this and compare the single coincidence window sorting algorithm with our spiking neural network, we can see that there's a configuration in which the SNN performs even better than the classical algorithm. Not just that it's able to predict coincidences better, even just slightly better. The inference time that it took us to evaluate this data was massively reduced when we used the SNN. As I mentioned, this is kind of the thing with single coincidence window solving algorithm. It's rather slow. This took over even when we looked at the Saphir dataset, where the acceleration was even, which was significantly improved. The only other thing we saw is that in this case, actually, the single coincidence window solving algorithm performed better than the SNN slightly in terms of the F1 score. This can have separate reasons, several of them actually. One of them, which we theorize, is just we trained both the Saphir dataset and the clinical dataset on the same number of samples, but the Saphir dataset uses many, many more crystals, so it has a much larger parameter space. So it would have made sense to just train it with more of this. Why we didn't do this, I'll get to in a second. In general, overall, when we looked at these results, we thought for ourselves, these are very, very promising first results, and which show we can use SNNs very nicely for this kind of problem. But of course, a bit of a broader evaluation would be needed for this purpose. So like PET is a very large field with a lot of detectors with largely different numbers of crystals, like much more than what we have in the Saphir dataset and much less than we have in the clinical dataset. A lot of different dose concentrations or spike rates in this case, and also source distributions. It would be very helpful if we just like evaluate a bit more, try out a few different combinations. The reason we didn't do that is because what we observed was that the training in this case was very, very inefficient. This might just be because we are not experts in spiking neural networks in general. And as an NTorch, in this case, it didn't support a sparse implementation. But like the training was very resource intensive and very energy intensive, which kind of would initially go against the promise of spiking neural networks in general to be, well, energy efficient. If this could be taken out of the way, in our eyes, there's quite a large number of other applications that we can actually use spiking neural networks in this case, specifically for particle event detection. In PET, for example, we have situations where you have an incoming photon which hits a crystal but doesn't deposit all its energy, but just scatters and hits a second crystal. In general, sometimes you discard these events or there's analytical models to recover this, but a spiking neural network would, in principle, be very easily able to just recover these hits very, very quickly, which would be very nice. But in general, this and also like coincidence detection in general are just, well, very specific examples of particle detection applications, which in high energy physics and particle physics, you have quite a lot. This is essentially a level 2 trigger. If this can be converted into the realm of, well, high energy physics, that would be something which we think is very, very helpful and very, very interesting. Because like the sparse binary nature of SNNs kind of lends itself to this problem. But until then, I was very fast, dear God, but still, I want to thank you all very much for your attention. And if you have any questions, I'd be happy to answer them.